Okay, next up we have Yu Yao, where he will be talking about how to combine timing constraints in message passing protocols and semantic foundations for this.
Thank you.
Sorry.
Thank you for the introduction. So I'm here to talk to you about semantic logic relations for timed message passing protocols. So this is a joint work between Carnegie Mellon University and the good guys at the University at Buffalo. So I want to start by setting the scene. So this talk is about time. Time is an important element in computing. What do I mean by that? Well, computations takes time. And computations also need to be on time. The first notion of time is captured in the notion of cost. It is the intentional property of the program. But that's not why we are here. We are about the second one. This work is about specifying, programming, and verifying timeliness of computations using type theoretic methods. So what do I mean by timeliness? I would like to introduce that with examples. So this is a protocol description that I take out from the documents, which says your SMTP server, which is your email server, ought to have a timeout of at least 5 minutes awaiting a command. So this specifies the condition where the command, timing condition, where a command or a message ought to be arrived. And there are actually more examples of this kind of specifications. And if you squint really hard, you will notice pattern. So every one of the examples have a verb, an action that talks about some sort of communication. And there's a condition which talks about when this communication ought to happen. So this suggests that we should think about a process calculus where communication is a primitive that is enriched with capabilities of copying about timing constraints. But that's actually not it. The systems we were talking about here are almost always heterogeneous. Now, what do I mean? I say heterogeneous in the sense that the system is made up of components that are not written in the same language. Sometimes you don't even have the code for the language, but you do still want to be able to provide whole system guarantees about the timeliness. So whatever we do, we have to account for that. Toward these end, this work contributes a process calculus and an operational model that allow you to capture the execution of timed message passing programs. So you have messages goes around and happening at specific times. And we also distill a specific specification language for these timed protocols. And we are in the form of session types. So we're enriching session types to allow them to specify timing constraints on top of their capability of specifying communications. And we tie these two things together using logic relations. And we strongly believe that the logical relations development is the heart of this development. Because we strongly believe the logical relation development is the heart of this work, because through semantic typing, we are tying together this automatic verification through type checking in composition with some manually verified components and provide you a whole system guarantee. So to get things started, I want to start with a crash course on intuitionist linear logic session types. So these are process calculus. So in these systems, here we have two processes. There is a sensor and there's a controller. The controller is like Google Nest, like think your home system controller. And these are the two processes in our system, and you connect them with a channel. The channel is a bidirectional channel in the sense that the message can go both ways. And the types in these kind of systems, types specify the protocol on the channel. Who ought to talk to who, then what's next. The intuitionist nature of the system gets exposed in the way that the channel differentiates a provider and a client. And in the intuitionist setting, when you specify protocols, you're specifying exclusively from the perspective of the provider. So if you say send, you mean the provider send. If you say receive, you mean the provider receive. So that's the intuitionistness of the system. And what kind of protocols are we talking about exactly? So here is a protocol diagram. So these states are called protocol states. And the edges on the arrow talks about what operation or message ought to happen to move to the next protocol states. Question marks means receive. They're called queries. And bends are called shrieks or sends. And the Letters means labels, and the v underscore something, these are values, functional values. So this describes the protocol of the sensor, and there are basically two branches. And first, it asks you to make a feature selection. So you can either ask for only the temperature data, or you can ask for the temperature data along with a air quality data. So our goal here is to associate each protocol state with a type by building it up gradually. And we want a type that specifies for the entire thing, so which means we want a type for the initial state as 0. So the first step of, so here the green ones are basically the state that we are currently in, and the yellow ones are next states. So the first, we say A0 is ampersand A1, A2. It means that A0 is a choice for the outside world to pick between two possible choices of features. On the left-hand side, you have S1. That means we are taking only the temperature data. So let's go with that path. So on S1, the protocol says, the sensor will send you the measurement data, then continue with S3. That's what this band tau temps means. Now we are on S3. S3 just means, oh, I'm going to send a closing signal, and that's the end of protocol. So that's it. And we do the same specification, do the same dance for the second branch, where the protocol says, oh, I'm going to first send you the temperature data, then I'm going to send you the air quality data, then I'm going to close consecutively. Now we put the times in. So due to the construction, the sensor requires 30 milliseconds to warm up before taking the temperature, before taking the air quality data, and requires 20 milliseconds to cool down. So how do we accommodate this in our types? Well, the way we do this is we annotate each type connected with T.P, basically a condition, which says this communication can only happen at the time T that satisfies the predicate or the condition of the proposition P. And so here we are saying that T3 is greater than T2 plus 20. T2 is the last time that anything is communicated. So it says, well, the next communication need to have at least 30 millisecond spacing. And here, similarly, T4 is greater than T3 plus 20, meaning, oh, you need to wait at least another 20 milliseconds after the last communication. What you notice here is the binding structure. No, we are not, like, the binding structure allows you not only specify the constraint, but also bind the time of communication. So the next time you can use that to specify what ought to happen the next time. We do have a type system, but we don't have to. I think the core of the talk is logical relation. So let us go into semantics directly. So we set up the semantic system using operational semantics. And the key idea here is you want to think about the execution of the system as a sequence of instantaneous communication steps happening at increasing time. So you have these like each of these instantaneous time, each of these steps happen like T1, T1 prime, T2 prime, T2. These are all instantaneous, but the time they happen are increasing. And we formally capture this by two components. One, there is a timed multi-step reduction judgment, which says, oh, you start with this time, this configuration, end up with that time, that configuration. And the way that we handle these instantaneous time is using a timed label transition system, where the upper part of the alpha is the action of the step, and the lower half T means at what time the transition happened. So this is a pretty box standard label transition system, except the key rule, the communication or synchronization rule, says to synchronize, both sides need to synchronize at the same time. This is important because in our system, if you're a provider, you are allowed to specify a time that you want your communication to happen, and we are only allowed the transition if the time that the transition happens satisfies the condition. That's what's on the bar. And if you're a client, you get to pick what time that you want to happen, and the transition is guaranteed to happen only at the exact time you pick. So there is no wiggle room in the dynamics. Now, because the synchronization rule forces them to happen at the same time, there is no ambiguity in terms of which transition at what time the transition happens. It is guaranteed that it satisfies both the condition set and satisfies the wants of the client. We're now moving to the logical relations. The goal of the logical relation, as we said, is to support verification of foreign code. So the key insight here is a notion of semantic or behavioral typing, where types are really classifiers of program behaviors, and in our case, classifies both the temporal and the communication behavior of processes. In these proofs, you have fundamental lemma, which basically turns a syntactic well-typedness judgment into a semantic entailment, which says, as long as you're giving me components that we know are semantically well-behaving, you can compose them with other components and get a whole system guarantee. So this is important, exactly because the assumptions can be established in any way possible, using model checking, using multi-party session type, using any method that you want. As long as you can show it satisfies the semantic requirement, you can put it together with another piece of code that you're either written in our language or not, and you get a whole system guarantee that is very strong. Now, our logical relations consists of 4 main definitions. This is a lot. Usually one logical relation is enough. Now we have 4. But don't worry, we will break these things down into pairs. So the first pair is the left half and the right half. So we call these things latent versus urgent interpretations, denoted by the letters L and V. So these are like these expression and value interpretations. So the urgent interpretation says the configuration must be able to do the communication right now without any passage of time. And the latent interpretation says that the configuration is capable of doing something in the future with allowing the passage of time. Now, to account for the passage of time, the latent interpretation requires you to externally submit these called computable trajectories, which describes how the transition transitions through time as a witness. And it is exactly the treatment of the witness that enables the second dualizing pair, which is the upper and lower half. And we will talk about how this works later. But the important thing here, we have the star interpretation, and we have these like non-star interpretation. And the star ones can be think about the interpretation being seen as needed, and the green ones are stronger. These are like as guaranteed. We'll get into that later. I would like to start with the urgent interpretation first because it's more straightforward. So here it says the configuration omega ought to behave according A1 external choice A2. This external choice behaves very much semantically like a conjunction at a Carnegie product. So it says a configuration omega is right now acting as this type if it can receive a label left and reach some omega 1, and we know omega 1 is behaving according to A1, and so that's the conjunction part, that it can receive labels right and reach some omega 2, and omega 2 is behaving according to the second component. So this is very much behaves like a Cartesian product, and the labels can be thought of like sending them with the projections that you want to take. Now with that said, now we can move on to talking about the latent interpretations. So these, as I alluded to, the star ones basically says omega is good as demanded from the perspective of one particular client, and the non-star ones are giving a much stronger guarantee that's saying it's good just as guaranteed straight up, and will be set up in the way that the non-star one actually implies the star one. I think it's actually better to understand these in terms of the proof obligations they ought to satisfy. So these star interpretations, we call them future proof, because it says if you have a promise today, the promise still stands tomorrow. If you know something that is good today, you move time forward, you don't suddenly lose the guarantee. It's still good even if you move time forward. So in that sense, a guarantee as established is future proof. Now, dually, these provider guarantees, these non-star versions, requires a much stronger version that is dually past proof. What it means is, if you know something's good at t prime, and you know you can get to t prime from t by doing some computation, then you can backwards extend the guarantees to a past that is t. So the star ones allow to move forward, and the non-star ones allow to move backwards. And if you know the logical relations, the non-star version basically only requires forward closures, and then the star versions here essentially is doing a time generalized version of the backwards closure. So you are closing backwards, but you're closing not only just transitions, but also time. And this shows up in their formal definition as this adjunction-like structure, where in one case, in the star version, you say, oh, I only need to guarantee any time that is in the future, I need to be good. But the other side, you are saying, oh, anything I'm quantified over, I'm not bluffing. I'm saying I'm only quantifying I'm only talking about things that can actually be reached. Everything I talk about is in the future. So I think this is a very constructive view where any claim that you make has to have like computational evidence to back it up. You cannot make an argument to say, oh, I will do this yesterday just because your client cannot get to yesterday. So our work is, I think, I want to talk about related work. Our work is understood in this general context of 3. You have these session types, and the one that's most related is the intuition linear logic session types. You have other methods using multi-party session types and using time automaton to do verification with time systems. And our use of logical relation reminds us their use in the Iraci framework, in Rust Belt, and more recently dim sum, which also uses a label transition system to support foreign code and stuff, and also reminds us of semantic typing. So in conclusion, we propose a process calculus and type system for writing and verifying programs with timing constraints. We validated the semantics with logical relations. Our system supports compositional reasoning of timeliness, automatic verification through type checking, and you can put these things together using logical relation to have to verify opaque components and have a full system guarantee. There's a concrete example that's in paper that I welcome everyone to check out. Our future work wants to incorporate costs, like the intentional aspect of time, into our framework. So you're allowed to say that, oh, I will make this deadline even considering that I'm going to spend this time computing the output. And we also want to support periodicity, that something happens over and over again in time through the use of recursion. What else in the paper? We have a type system actually set up that matches very closely with the semantics. You can see how we basically go from semantics and we internalize all these semantic properties into syntax using a type system. And we have these like compatibility judgments allows you to move a type between the stronger star guarantee to non-star guarantee and back and forth. And we also have actually pretty algebraic treatment of how we manipulate computable trajectories. These are the biggest part in our proof. These algebraic operation contributes a lot. And finally, we actually have a DSL implemented in Rust. We have a lot of timing constraints to discharge, and we discharge them with SMT. This works pretty surprisingly well, I will say. And we have, like I said, the full-fledged sensor example in the paper. Thank you.
Oh, I'm actually curious, and perhaps I missed it, but do you consider real time or discrete time, like all these semantic relations?
Oh, so the way that we set up the logic on time is actually pretty free, is basically whatever you like. Mm-hmm. You just need to have some basic assumptions, like for example, you validate transitivity and stuff. Our system right now only checks the discrete time, and then actually it needs to be natural number index time. It's not even full integers, but it is possible to extend to a real-time situation, but you would lose probably, like for example, a lot of the benefits you get from the SMT solver.
Right. Okay. Thank you.
Sorry. So you treat the unary logic means that you are not doing binary logic, which means that you are not investigate semantics equivalence or time to semantics equivalent, right?
That is a very good point. We do have plans in the future to extend it to a binary situation to capture like equational reasoning and stuff. I think the unary one is a good start, and there is already a lot of like constructions. For example, we need to figure out how to algebraically treat like trajectory and stuff. So I think this is a good first step.
I had a question about the next slide, I think. Yeah, so here, the definition of V on this and, I was expecting it to have V on these parts, but it's using L instead. Is this a typo, or is there something interesting going on here?
There is. So generally, when you set up this like expression versus value, once you like the values only guarantee their topmost, like outermost behavior, and once you get through that, you peel that off, then what you're exposed is something that may be capable of running again. That's what this is exposing. We can probably set this up like more explicitly in a type structure where we differentiate, like we use like something like a fine-grained call by value calculus to make this more explicit. But we think this adds to complexity, but not really make the problem clearer.
But wouldn't this mean then that like it doesn't have a unit, for instance? Like if you had A1 and false or something, then that wouldn't be equivalent to A1 because A1 and false would introduce this additional stepping action.
Oh, okay. So what happens is at the L interpretation, like the latent interpretations for the unit types are. I need to be very careful with this, but very close to being an actual unit, but not quite. I think this will be much clearer if we actually separate out the semantic domains more explicitly. But here's what we did.
Okay, so rest of the questions can be delegated after the last talk.